Good afternoon, everyone. Thank you for joining us. My name is Marissa Waterman. I'm the Marketing Director here at the Academy. Here with us today, we have Scott Warren and Kate Despinoy from Stanley Consultants. We also have Chris Bergeron from Sewerage and Water Board of New Orleans. We will be discussing the ongoing challenge of New Orleans drinking water management. Also joining us today is Executive Director, Dr. Daniel Other. Dr. Other will serve as the moderator today. During the presentation, you'll be able to submit a question by clicking on the Q&A icon on the bottom of your screen. Before we get started, Dr. Other would like to say a few words. Good morning, Dan. How are you?
I'm great. Thanks, Marissa. I'm super excited to learn about New Orleans, the city underwater, and how it's being protected with levees and pumps. Of course, we are fantastically grateful for the patrons of the Academy. Their financial support helps the Academy run. So we've got the patrons here on our screen. They support the Academy in so many ways. In particular, I want to highlight the sponsor of today's webinar. So Stanley Consultants is actually sponsoring a number of webinars for the Academy, including today. And so thank you so much to Stanley for sponsoring webinars for the Academy, and in particular today's. Today, we're going to be hearing about a city underwater, the ongoing challenge of New Orleans drinking water management. And when I was reading the abstract, there were some things and I thought, wow, this is really interesting. I didn't realize some of these, but on reflecting, it makes sense. You know, half of New Orleans sits right there at sea level or below sea level. Parts of it are actually continuing to subside, and some rates are as high as 2 inches a year. Of course, New Orleans gets hit by hurricanes as well as just storms, and there's an extensive flood protection system of levees and pumps. Now, that system is challenged regularly, not only by Mother Nature's fury, but also operators overcoming antiquated systems, various components that need to work together. And so today we've got three fantastic speakers. We're going to hear from Kate Despinoy, Chris Bergeron, and Scott Warren. I'm going to introduce a little bit about each of these three. Kate's a senior environmental engineer with Stanley Consultants. She's in the firm's Chicago office. Kate is a client service manager, and she's a senior engineer in the water and wastewater group. She has domestic and international experience in the design of water wells and distribution systems, sewage collection, pumping and treatment facilities, drainage collection, and detention systems. We have Chris Bergeron, who manages the mechanical and civil engineering departments at the Sewer and Water Board of New Orleans. He's been there for the past 12 years, and his work includes large-scale projects, including capital projects, and one of those is the utility's future West Power Complex, which is a $300 million upgrade to the power generation facility responsible for pumping out water when those levees start to fill up and New Orleans becomes a swimming pool. The West Power Complex powers all that drainage pumping system for the Crescent City. And then finally, the third person who will be speaking as part of this trio is Scott Warren. Scott is the control system technical lead for Stanley. His experience includes extensive work with DCS and PLC-based control systems. He's got experience design, testing, and commissioning Emerson Ovation DCS and Siemens PCS S7 and Siemens S7 300 PLCs. So we've got three fantastic engineers who are going to explain a lot about a city underwater. Kate, Chris, and Scott, the stage is yours. Thanks for joining us, and thanks to Stanley.
Thank you. Good morning or good afternoon, depending upon where you are. And thank you for this opportunity to speak today. Stanley Consultants has been very fortunate to have the opportunity to work with the Sewage and Water Board of New Orleans over the last 12 years on some of the projects that we'll be discussing during this presentation. And then the 6 topics that we have listed here provide an overview of the content that we'll discuss today. Chris with Sewage and Water Board will be discussing the first few topics. First, he's going to provide some background on the Sewage and Water Board of New Orleans and the Carrollton Water Treatment Plant. And then he'll talk about some of the factors affecting the operation of their water system, both longstanding and post-Katrina. He'll talk about the iterative upgrade plan that was developed in cooperation between the Sewage and Water Board of New Orleans and FEMA. We'll talk about the finalized 3-phased improvement plan, which is effectively named the Water Hammer Hazard Mitigation Program. Scott will then talk about the instrumentation and controls design associated with one phase of the project. And on closing, we'll talk about the current state and the future improvements at the board. Now I'll hand it over to Chris.
Thanks, Kate. So to get started, a quick history of New Orleans and the Sewage and Water Board. Founded in 1718, New Orleans is one of the older cities, especially one of the larger cities in the South. But the Sewage and Water Board didn't really get started until 1893. We were formally founded in 1899. There was a 35-year period in that late 1800s and early 1900s where we, in the city, really invested about $1 billion in today's money towards the three systems of water, sewage, and drainage. Obviously, the drainage is one of the more highly publicized parts about New Orleans, as that is a big driver on everything else we do. So when you talk about the drainage system, we often talk about ourselves that we are a bowl floating in a larger bowl of water. So the picture on the left kind of illustrates this the best. The topography of New Orleans is below sea level, and to the north of us, we have our Lake Pontchartrain, and then to the south of us, we have the Mississippi River. If you go back to quotes from prior to the establishment of our modern drainage system, there were plenty of quotes saying that, you know, when the Mississippi River level rose, the entire city was flooded for periods of time, and then you had the high tides from the lake rising, and that was basically the Gulf of Mexico rising into the city from the north. So something had to be done, and in the late 1800s, the drainage plan came to be. The map on the right, I love to show this one. This is from the late 1800s. It's how the drainage system looked prior to 1897. All of that hatched area, that's everything in the city that's below the mean sea level at that time as they surveyed it. So without any kind of drainage, that part of the city is underwater. So at this point in time, the majority of the population lived along the Mississippi River because that is the highest part of the city elevation wise. So as we got into this in the early 1900s, we started building pumping stations. Prior to this, we had what they called drainage machines, which were a little more like water wheels that kind of move the water a little bit. But the early 1900s, especially in 1913, was when we became more of a, I'll say modern, and I do mean that in the early 1900s, a modern industry for moving water. This is one of our first drainage stations. Those pumps are about 12 feet in diameter. So when you start talking about the volume of this, we say they push about 1,000 cubic feet per second. That converts to about 450,000 gallons per minute. And when we talk about water production, when you talk about water, usually use millions of gallons per day. So that's about 650 million gallons per day. What that really works out to be is that one of those pumps can push about the equivalent of a Olympic-sized swimming pool in about 90 seconds. We have dozens of these throughout the city. These were installed in 1913 and they are still in operation today. So how does that affect the water production and water treatment? Well, if you look on the right side of that picture, those motors are a bit funky looking, and they are. Those are direct drive with exposed windings. To get a lower RPM with a higher torque at the time, since 60 hertz electric frequency wasn't the standard at the time, or it hadn't been established quite yet, we established it with 25 hertz motors. So these pumps run at about 93 RPM, and with the conversion with the poles and 25 hertz, it creates that slower speed direct drive. So as we move forward in our industry, we have to power these. There was no real utility that provided 25 hertz power, which brought us to our Carrollton water plant. So that is our main water treatment facility, and it also serves as a power plant. We have built over the past 100 years a steam turbine generation system. At the time, at one point in time, we had 4 steam-driven turbine generators. We have another natural gas combustion turbine generator, and then we've modernized it as we've gone on. But those steam turbines would produce 25 hertz. So we have feeder networks throughout the city that would power these drainage pumping stations. To piggyback on that, as we grew our water production, we decided to utilize that on our water pumps and our intakes from the river. So we take all of our water in this city from this Mississippi River, and then we treat it. We separate the river sediment, we disinfect it, and then we use a rapid sand filtration system still to this day. So in the early 1900s, 1908 was when the construction first started. We've been upgrading it ever since. But our first rapid sand filters were built in those teens, and they are still in operation today. So just to kind of show the geography of the city itself, we do have two separate systems that are separated by the Mississippi River. The East Bank system is really the north side of the river at where it comes across New Orleans, and it is geographically the extent of the New Orleans system itself. So all that blue on the north side of the river is our East Bank system, and then the dark shaded blue is our West Bank system. We have two separate treatment facilities and two separate sewage treatment facilities as well. So when you talk about the East Bank, it is 130 to 140 million gallons per day. The West Bank does significantly less, between 10 and 20 million gallons per day worth of treatment. So, and then this next slide will show you where our treatment plant is on the East Bank relative to the city. So it is all the way on that west side of that city. And we have to push all this water all the way out to that northeast corner, as you saw on the previous slide. So the facility itself has 3 pumping stations, which work out to be 8 different pumps. The fascinating thing about us is that at this time in the late 1900s and early 2000s, we had no elevated storage. We pump water from this facility all the way to that northeast area without any booster pumps and no elevated storage. The topography of the city allowed us to do this. We are a flat city. We don't have any hills. There's none of that really. The elevation change is a couple feet here and there for ridges that were natural geography of the city at the time. So having consistent pumping was incredibly important to us. So these 3 pumping stations, which have 8 pumps, we diversified the power source on them. So our Claiborne pumping station, which is number 1 at the north side of the facility, has 4 pumps, 2 of them electrically driven by 25 hertz power and 2 of them by 60 hertz power. We generally used our 60 hertz pumps fed by the utility, the local utility, but we do not have a high voltage transmission line into our facility. We were pulling off the distribution grid, the same grid that the neighbors use. So any brownouts they would have, we would see the same effect. So our second pumping station, number 2 over there, it's Panola pumping station. A little interesting on that one. Each of those pumps has 2 motors attached to it, which allowed us the flexibility to run either from our own internal 25 hertz power generation or from the utilities 60 hertz generation. And then our third pumping station, our high lift pumping station, again, as I said, we had these steam turbines, which means we had boilers, and we just pulled right off that power plant and decided to convert our pumps into these steam driven turbines. So at any point in time, we would have 3 different sources of power, potentially 4. As we became a more modern utility, we started figuring out how to produce 60 hertz power as well. So there was that 4th option for us to produce power for that reliability. Because there's this, as we grew as a utility, and as really the federal agencies have regulated water, as these regulations became stricter, we learned more about it, right? At the time in the early 50s, if we had pumps shut down, it wasn't that tremendous of a problem. You'd start it back up and you'd get back into it and you'd raise your pressure throughout the city. But with the Safe Water Act and other local regulatory agencies in Louisiana, it's the Louisiana Department of Health, they started to regulate minimum pressures in your system. So if your pressure throughout your system drops below, at the time, in the early 2000s, this was 15 psi, you were required to issue a boil water advisory throughout the city. These are becoming more prevalent in most utilities, as we've learned a lot that people would always say, well, we didn't have those in the early probably 80s and 70s. Well, it's because it wasn't really required to issue them. Those agencies are starting to get stricter and stricter, and as your monitoring gets better, these restrictions are easier to see if you're following them. So, and the idea behind that is if your groundwater is a higher pressure than your pipe, then theoretically that groundwater could get into your pipes and contaminate the water. So even if it's for a second, you're compromising the pipes potentially and the water that people are drinking, so that advisory is to be safe for everyone to just boil your water until the utility can confirm that that water is safe to drink again. So in the early 2000s, we are now looking at 100-year-old facility, most of it original. Our Claiborne pumping station is our newest facility, built in the late 50s. So we're struggling with maintenance, with capital upgrades, and then of course funding, like every water utility I think in the country is. And what was the last thing that we needed to happen to us? And it was a Category 4 hurricane that devastated the Gulf South. Um, a day that really lives on in this city forever, which is August 29, 2005. The documentation of what happened that month is all over. Loss of life, loss of property, the relocation of hundreds of thousands of families throughout the Gulf South can't be overstated. But this topic is about water, and how did Hurricane Katrina affect the water treatment and distribution system? Well, we were struggling with leaks throughout the system prior to Hurricane Katrina. We were estimating we were losing somewhere between 30 and 60 million gallons per day throughout the system with water leaks. With the city holding water for weeks at a time before we could drain it with the broken levees, there was no way for us to drain the city until the levees got fixed. So you had this saturated ground, you had this water sitting on top on all the roads and just creating this pressure and infiltrating the pipes. And then we finally got everything drained and we needed to start producing water again. The immediate aftermath that we were finally able to get everything settled, probably about a month after the incident, is when we could probably start to really get our handle on some things again. We started noticing we were losing a lot more water. Our estimates were 30 million gallons per day more in leaks throughout the system than prior to the storm. Some pretty significant. And then FEMA came to us with this idea of our water line replacement program, as we call it now. So we've identified all these leaks. We've identified that it's significantly more, and FEMA came to us and said, let us help you. We will help you get back whole prior to the storm. So we will help you fix approximately 30 million gallons a day worth of leaks. Over the 3.5-year period after Katrina, we fixed over 28,500 leaks ourselves as a utility without any help. That's about 20 repairs daily, every one of those days. And that's not accounting for the extra leaks that were occurring every day. So we were getting behind, and fixing 28,000 leaks was not enough, and we were still losing water throughout the system. To compound that, we as a facility trying to generate our own power and the local utility trying to generate their own power was struggling as well in the aftermath. The estimate is that in that same 3.5 to 4 year period, we experienced over 500 power outages, either from our own power generation or from the utility. Now, if you remember, I said that these 8 pumps serve the entire city without any boosters and without any storage, elevated storage. So when we would lose power, the pump would shut down. Our swing check valves were in place to protect the pumps from high pressure transient across the pump. and that swing check would slam close. And that slam would create a water hammer effect that would just make its way throughout the system, hitting every joint and either creating new leaks or exacerbating additional leaks. So FEMA came to us again and said, hey, look, we're helping you repair all these leaks. Why don't we help you try and mitigate new leaks? Because we're kind of in this cycle of we're fixing things and you're getting more leaks and we're not really going anywhere. So they came up with this plan. If that's your problem, if you're losing power and your check valves are slamming closed and it's creating new leaks, why don't we help you buy new pumps? Let's buy new pumps, new votors with variable frequency drives so they start up slowly and they can shut down in controlled manners, even if there's a power outage, and then have those isolation valves close, not in a disruptive manner, but in a controlled manner with a slow closing valve. And then we can help you create a new priming system so that you can start immediately instead of trying to pull a prime every time you want to start a pump, which was taking us between 3 and 5 minutes just for the priming, because we were using our original vacuum pumps for most of these stations. To prove this, they asked us to go through a surge analysis scenario. So what does all this really look like in the system? And we worked with Stanley Consultants, who was our designer, and they had another consultant, Owen and White, who performed their surge analysis for them. That okay, let's build all the scenarios. What does this system look like? If we were running 5 pumps to keep our pressure at 72 psi or 70 psi, what's the worst case scenario? Well, we said, well, that would probably be if we lost both sources of power and we still had a steam pump running. And at our peak demand, what does that look like in the system? So they used our existing model that was mostly complete. I wouldn't say it was 100%. But they gave us a really good idea what it looked like. So when you build this water model, you basically select where your pumps are in your water source is. And we had about a dozen nodes throughout the system that we ran these scenarios through to see what's the real effect on it. For this presentation, we're just going to show you one node and what that looks like. So this is about 10 miles away from our water treatment plant. It's about halfway from the plant to the furthest points in the system. And if you think about a wave on a graph, if you lose 1 psi at the plant, you're losing a couple psi a couple miles down the road, and then as you get further, that just gets that disparity gets greater. So when you talk about a water hammer effect, it may and should be a little more drastic as you go further. So first scenario ran. What if we lost 5? What if we had 5 pumps, we lost 4 of them in our original scenario? And then if with FEMA's proposed plan, what would that look like? Well, these are 2 separate graphs, and I know they don't look like that. This is just kind of prove that while FEMA's ideas were valid and could potentially help, in our worst case scenario, it did not do much. We were still dropping below the boil water threshold within a minute, and you were still seeing that noise at the bottom as the pressure actually started turning negative and water trying to push back towards the plant because of that, because of that surge. So we came up with an alternative scenario. What can we do to try and stabilize that pressure? And there's really only 2 strong solutions here. First one was bladder tanks, which you could just use a pressurized tank to try and keep the pressure stable. At this magnitude with 130 million gallons per day at this pressure, it really wasn't a feasible answer. So your other alternative is to put water in the air and let gravity do the work for you. And so we're choosing between standpipes and elevated storage. Because of the scenarios that we had to run, the standpipes didn't particularly serve our purpose because we needed more volume higher in the air to keep us going for that period of time. So we selected elevated storage and decided to run that scenario. So here's that same graph, or a very similar graph. So this is with FEMA's proposed upgrade on the left, and then with the elevated storage. Now note that the scale on these graphs are very different. The first one ends after 2 minutes. The second one ends after 40 minutes and is still going. this was a clear, great decision for us and a great option for us as a utility. With 2 elevated storage tanks at our Carrollton treatment plant, we could lose 4 of our 5 running pumps and still survive for 40 minutes with 40 psi halfway across the city. So we brought this back to FEMA. This whole plan started in 2011. By about 2014, we had gotten an answer from them that, yes, let's do it. We can do it with the new water towers located on our plant. We had to tweak some other things. They proposed new pumps for us originally, but our old original construction didn't really allow to replace pumps. We had to rehab our pumps in place. So 4 new motors with VFDs at our Claiborne pumping station, and then new valves and meters throughout. So we established this plan with Stanley Consultants, and we split it into 3 phases. The first one was to get our 2 elevated storage tanks at the plant, which posed its own problem because they had to be close to our pumping stations. They had to be the closer to the origination of the water distribution, the better for us. The more time we got and the less transient surges were put on the system. So when you talk about design of them, you're talking about 2 million gallons each at about 200 feet tall. The math here is pretty straightforward, which was 40 minutes of time over with about 440 million gallons per day works out to be about 2 million gallons. The 200 feet tall was based on the pressures that we were using at the time, and we decided to go aesthetically with the composite style, really only for the looks, as we are built in a residential neighborhood. So we tried to do this as least disruptively as possible from the skyline perspective. From the hydraulic side of things, it's a fairly simple idea. You put water in the air and you try and keep it there. There's no inlet or outlet here. It works, I want to say automatically, but it works as it does. Water rises at the rate of 2.3 feet at every pound of pressure that's on the system. So if it is tied directly into our system, there's a 54-inch pipe that fills and drains the tank. There's no inlet, there's no outlet, it is one pipe. So it floats on the system. If there's a sudden drop in pressure, you'd say that the water in the air catches that low pressure and kind of stabilizes it. When we talk about building it, we're building it on a 100-year-old facility. And this next slide is one of my favorite pictures to show how we had to do this. Being, again, 1908, we didn't have very great record drawings, but we knew this was where we needed to build it. The dark lines are the proposed drawings. The blue lines I highlighted are the existing water lines, either high pressure or low pressure. And then red is our underground feeder network, because we're also a power plant that is trying to run underground feeders throughout the city. So trying to stick a huge structure in the middle of this was an incredible challenge logistically and from a design standpoint, but we got to do it. 2016, we really started to get to work on this project, and I had the luxury of being able to watch it outside my office window. A fascinating structure, about 130 to 140 auger in place piles with a significant foundation, and then watching this contractor build it in 7-foot lifts all the way up on the concrete, and then build a steel tank around it and lift it up. Over a 2-year period, it really was a fascinating experience to watch it be constructed. We had these towers completed in the mid to late 2018 and then early 2019, because we did build 2 towers and we tried to get them done as close as possible together. And we saw the immediate benefits from pressure losses with our system, because our pumps were getting less reliable as they aged. And we have seen those effects incredibly. And it's been one of the biggest benefits for our utility, at least especially from a visible standpoint. But that was phase 1. And I'm going to hand it off to Kate, who's going to talk about phase 2 and 3.
So the Claiborne Station is the most recent station or recent project that's been completed under this project. We had substantial completion in late 2022 and then this past spring final completion. Claiborne, it's the largest of the three stations and it was originally constructed in 1958. And here on the slide, you can see two elevations that I've taken a snippet of from the original drawings, west and north here. And before I jump into the improvements that we did at the Claiborne Station, I'm just going to reiterate a few things that Chris mentioned earlier. The three pump stations, they distribute potable water into one pressure zone. And the water level in the clear wells, and if you're not familiar with that term clear well, it's essentially a reservoir. It's the basement of the pump stations where the water is pumped from, is at the same elevation throughout the plant and is balanced through a series of pipes. And the water that feeds the clear wells is from the Sycamore and Claiborne filters. The Claiborne filters are here and then Sycamore is here. And to reiterate, the peak pumping capacity of the three stations is 170 MGD, and pressure is typically maintained in the system between 68 and 72 PSI. So at the start of this project, with the Sewage and Water Board, the staff consensus, we agreed that the rehabilitated pumps would continue to match the previous flow rates. And from this table, you can see the flow rates ranged from 41 to 45 MGD. I'm gonna put my laser on here. So for our design, we utilized original drawings and performed a lot of on-site as-building. From this drawing here, you can see that we have a split centrifugal pump. This is one of the cross sections of one of the pumps. And then we've got a suction here that goes into the clear well below. On our discharge line, we have a tilt dish check valve and gate valve. Here are two photos within the station prior to the rehabilitation. You can see the motors here in the front. And then in the back of the photos, you can see the two pumps facing each other. I'd like to note here our stamp, who that, and that's an alternative pronunciation for who's that. For those of you who aren't familiar, it's the chant of the team to support the New Orleans Saints. Chris will have to confirm, but I'm pretty sure that was probably placed on there sometime around when the Saints won the Super Bowl back in 2010. It hasn't yet been returned onto the motor, so maybe soon. Talk about some of the improvements here. Here you can see the existing pump being taken apart. We had significant rehabilitation of the existing pumps. That included new pump impellers and shafts. They were removed, scanned, and rebuilt. We also had anti-reverse ratchets for all the pumps, and that was to prevent rotation from and potential damage to the motor. And this was associated with the new ball valves, which allowed for slower closure. Additionally, we have new electric motors and VFDs to regulate discharge pressure. Here in this photo, this is an active construction photo here. The contractor's team is removing the existing impeller to have it shipped to Xylem to make a pattern for the new impellers. This occurred pretty quickly towards the start of construction. Beyond the impellers and the shaft, the bearings and couplings were also replaced, as well as a lot of the internal guts of the pump. You'll notice the dates here on the photos, June 2022. Notice to proceed had been given several weeks prior to the start of COVID. COVID did initially obviously slow down work early in the project because the first couple of weeks, everything was shut down. Then for a while, there was still obviously some unknowns and concerns about the spread of COVID. However, policies were developed and construction continued, knowing ultimately that the project had some deadlines set by FEMA. Here's another construction photo showing the removal and clearing out of some of the older electrical and controller equipment. This provided much more floor space and future working space for sewage and water board staff. So you notice the building is quite long and slender, so maneuvering is quite difficult with pumps and motors of this size and weight. Here you see an updated cross-section taken from the construction drawings. Some of the additional improvements included air release valves. We also had the installation of actuated ball valves, which replaced the original check valves. These ball valves allow for the pump discharge lines to have a variable step closing feature, so you could adjust the staggering of the final closure to prevent closing of all the valves at once in the event of a power loss, to help with some of those water hammer issues we talked about earlier. Prior valves, as I mentioned, were weighted and then would close quickly to prevent water from coming back towards the pump. Additionally, here we have a new vaults. Initially, or prior to, all of the valves and piping outside was direct buried. So the new vaults allowed for easier access to the meter. And here you can see in the valve cross section, we've got some pumps. You can see across the 50-inch diameter potable water line crossing. Additionally, you'll notice how close that this valve vault is to the street. I'll show you in a few pictures a few slides later. But here you've got your fence line. And then here you can see you have a sidewalk and then the cross section of your of Claiborne Avenue. So very, very close to the street. And here you can see actually in this slide where you actually have a few additional valve vaults here that lie under Claiborne Avenue. So the pump rehabilitation inside the pump station was only one part of the larger improvements needed to upgrade the facility. And we had to develop a detailed bypass plan that was needed to make the discharge header and interconnect improvements and then keep Claiborne station online. So Claiborne is a very critical station. It's the largest of all three stations, and all the Claiborne filter water goes through that clear well before it's either pumped out to the distribution system or flows into one of the other pump stations. So to prevent negatively impacting operations and compromising the potable water in the clear well, only 2 pumps of the Claiborne station could be taken down at any time. So when Claiborne was under construction, the other 2 stations, High Lift and Panola, were operable, as well as the Claiborne elevated tank. So it was a very, very complicated construction phasing. Over the next couple of slides, I'm going to try to simplify it, but give you a high level understanding of how this process occurred. Just to give you an idea of the coloring here, blue shows the flow, red shows any demo work, and then green shows any new installed work. So for this first portion of the project, we had to remove the 50-inch low pressure line that brought water from Sycamore filters over to the ground storage in order to make the necessary improvements. So to do that, a 48-inch bypass water line was installed. And then in this phase, you have that 50-inch line demoed. In the next phase, there was a temporary line stop installed to allow for isolation of the first 2 pumps, which are referred to as 510 and 520. It allowed for isolation of that header. As soon as that was isolated, the pumps 530 and 540 were quickly turned on to continue flow of water into the distribution system here. At that time, the demo work could begin on the discharge lines and the common header, and improvements could start on pumps 510 and 520. So here in green, you can see we have the improvements. The rehabilitation has been done to the pumps. You have the new 30-inch discharge lines, new valving, new meters, new meter vaults, as well as new header that's connected into our water tower. And then here, gate valve ready to be connected to the second round of improvements to pumps 530 and 540. So after acceptance testing of 510 and 520, they were able to be brought online. And then here you can see mirrored work could begin on 530 and 540, similar installation. And then following acceptance testing of 530 and 540, you could complete installation of all the lines in an interconnects to bring the pump station fully online. And here are two construction photos that sort of demonstrate what that looked like. Here you have your meter with the rebar set up for the vault ready to pour the concrete. And then similarly here in the second photo, you have your two isolation gate valves, again with rebar and concrete ready to be poured pretty soon. You can see where the meter vault is very, very close to the face of the building here. And then you have your isolation valves that are actually here sitting underneath Claiborne Avenue. So the installation of all this new piping and vaults was probably one of the most difficult parts of this project. As you can imagine, like many construction projects, there were a lot of unknown utilities causing a lot of conflicts. So during this phase, there was a lot of investigation work that went on to determine where these conflicting lines, they were still active, and where and how we could reroute them. And then going back into the pump station, I'm going to talk a bit about the vacuum priming system. For those of you who aren't familiar, the vacuum priming system is used to pull water into the pump, which then allows the pump to start. So it does this by creating a vacuum that extends from the top of the impeller down into the water level of the reservoir. And our priming system was sized to maintain a prime across all four pumps even when the pump wasn't running, to eliminate any significant downtime it would take to start pumping. And this was a requirement to provide pump starts on demand because instantaneous pump starts prevented some of the low pressure surges that we were talking about earlier. And this vacuum priming system, it has two vacuum pumps, one duty, one standby. You can see here we have the 2,000-gallon vacuum receiver. Initially, when we started the vacuum priming system, we did have some kinks to work through because obviously we were only bringing two pumps online initially. And the suction was significant enough that it was pulling on the level switches, which was triggering some alarms. So we had to throttle the lines down a bit initially. Some additional improvements included a surge control facility, and this was part of the recommendations from the surge analysis. It added a remote surge facility several miles away. Within this building, you had two 1,000-gallon surge control bladder tanks, one serving as a backup. And then additionally, we had our VFD building, the picture here on the right, which Scott will show some pictures of inside in a few minutes. And we had some switchgear electrical improvements. So as part of the project, we had the president visit in the middle. President Biden wanted to tour and highlight the Sewage and Water Board of New Orleans as a prime example of a facility that's in dire need of modernizing its infrastructure. And the president, during his visit, specifically named the Sewage and Water Board of New Orleans in his $2.2 trillion proposal to revamp the nation's infrastructure. So you can see him here, and then you can see part of the vacuum priming system is complete here, and obviously still in construction on this side. So as I mentioned earlier, during construction, we were working in the eastbound lanes of Claiborne, and to accommodate that, there was a significant lane shift during construction. This first picture shows some of the open trenches for the discharge piping and improvements. You can see that it's quite intricate, a lot of work going on out here. You can tell that the work was extending well into these lanes here. In the second photo here, this is following completion of construction. You've got a teeny strip of grass, you've got valve vault access here, and then your fence line and sidewalk, as I had showed in that previous cross section. And then here is once Claiborne was open, you can see back to normal. Here are a few additional pictures from project completion. Not that it changed too much, as the pumps look mostly the same, although you've got new motors here, but you can see that the space is much clearer and open. And then on the picture on this next picture here, again, another picture inside the station, and then you can see the vacuum priming system here, and then just another angle of the front of the rehabilitated outside of the building, and then you've got the water storage tank there in the background. So now we're on to the third phase of the project, which is improvements to the Panola and high lift station. We're currently underway on the Panola station, and then following its completion, we'll start with high lift. Here's a cross section of the Panola station. You can see very similar looking to the Claiborne in terms of how it's set up. So here you've got two existing conditions photos to the right. The improvements will include rehabilitation of pump 1. Pump 2, it had significant repairs done a number of years ago, but both pumps will have very similar improvements to Claiborne, including new impellers, new increased shaft size for those anti-rotation devices I mentioned earlier, a new vacuum priming system, and some of the additional improvements that I've got listed here. One additional improvement is we'll be doing a structural lining of the clear well. Unlike Claiborne, however, Panola Station can be taken out of service to isolate the facility during construction. And while it's out of service, the high lift pump station will be providing water to meet the demand. And on this next slide here, we've got two active construction photos. This project is set to finish in August of 2024. Now, touch briefly on the high lift improvements. These are two photos here on the right. Those were taken at the start of the project when the team was there. You can see that the team here in the background on the first picture. At the time of the start of preliminary design on this project, the high lift station was being renovated with some improvements, and there was rebuilding of the pumps and steam drives. But during the design of the project, one of the pumps had been converted over to an electric motor. And under this project, we'll be doing the same. A second pump will be converted over to a soft start motor. So here again, very similar improvements to the other stations. We'll have replacement of the impeller and shaft. At this station, we'll only have some modifications to the vacuum priming system, however. And now I'm going to hand it over to Scott to talk a bit about the Claiborne pump station controls.
All right. Thank you, Kate. So I'm going to talk a little bit about the Claiborne pump station controls and how we designed a system from a blank slate. So I want to start with what is instrumentation and controls engineering. So instrumentation controls, or INC as it's sometimes lovingly called, is sort of a unique discipline. We interface with process engineers, and sometimes we are the process engineers or the mechanical engineers. We work alongside with them to determine how the system should function and what instruments or measuring devices are needed to make the process do what we intend. Then we interface with the electrical engineering side, and we work with them to determine how the electrical equipment will control the mechanical parts and how electrically it will work. And we also interface with the client to determine their requirements. So this is an iterative process, but at the end of that, we mold all three together, and ta-da, we have a controls design. So we start our designs later than most disciplines and always finish last. So we're the last out the door. on a project. A controls design is very personal as well. So I guess what I'm saying there is there's no specific formula for the outcome. It's based on client preference and design constraints of the other disciplines. So I want to talk a little bit about the history of the controls at Claiborne Station. So as you heard earlier, the pump station was built in 1958. And that was 11 years before the first programmable logic controller was even developed. The pumps were started and stopped via push buttons and pistol grip switches on electrical switchgear and control stations that were placed throughout the plant. An example of kind of how this worked was a drawing I've got here, a snippet from the right. It sort of details how controlling electrical equipment happened back in the 50s, the wiring of contacts with a sequence of events written in plain English, give or take, explaining how the system should work. So the electrical gear was upgraded over the years, which changed how some of the pumps were run, but there were no technology forward leaps on control system upgrades from the original plant design. A control system as we know it today did not exist in this portion of the plant. So here's some examples of manual control stations at Claiborne. The one on the left here, operators use this panel to close switchgear breakers and start the pumps, and then they would watch the voltage and current shown on the analog dials up at the top of the panel here. And then on the right, what we have here is a panel that operations used to start the vacuum system. On 2 of the 4 pumps at Claiborne, they were split in half. And this vacuum system, kind of like Kate said earlier, it draws water up from the clear well to flood the pump case so that once it's full of water, the pump can be started. Here's one more example of an old control station we found in the plant. It's a wound rotor motor control panel. And how these worked was they would add or remove resistance in series with the motor winding circuit to adjust the speed of the motor. This one had 4 speeds at one time, but the panel was abandoned. And I would say this is fairly typical in plants where you have updates over time. Maybe something in the panel was needed all the time, or a circuit that couldn't easily be removed. And so it was easier to just leave the panel than it was to pull it out of the station. So the discovery process, we knew from the start that without a modern control system at the plant, this was going to be an uphill battle. We started our discovery in early 2012, once the project's kicked off, and then this process continued into 2016. And all the while this happened, we faced a number of issues, such as we had Sewage and Water Board employee retirement. So our water interface point retired, and then we had to start over again. We had plant operations doing maintenance and upkeep on some of this equipment, and then design changes that were based on other ongoing projects. We were not the only fish in the pond at that point. So the original drawings, and you can see on the right here, this is a picture of the drawing room. Everything's in paper, and they had started scanning these, but they weren't cataloged. They just had files of a bunch of files scanned. So it was near impossible to find the drawing that you were looking for. And really, in many instances, we didn't know what we were looking for, just something that was up to date. So the paper copies here, they were cataloged and stored by project number, not necessarily by year or location on the site. So that proved difficult in finding anything specific. So here's some examples of instrumentation that was in the plant at the time. On the left here, we have a chart recorder. This one, it recorded distribution pressure with 24-hour chart recorder discs, which is just a piece of paper that documented a continuous 24 hours of pressure, much like a historian or a data logging computer would do today. It's just the manual version of that. And they would have to change these discs every 24 hours. The pressure gauge on the right here is shown is at the roof peak of Claiborne Station. And it's approximately 2 feet in diameter and has a brass decorative plate around the face, much like you might see on a ship. This is nothing you can buy today. And here's just another view of that from the end of the station. So without a PC or any electronic readout, this was a quick way to walk into the station and immediately know if operations was on target. So the most important part of the discovery process was to meet with the Sewage and Water Board and to figure out how things work. And some of the things that we needed to understand were, how did operations start a pump without a control system? How did the controls that they had function? And of the auxiliary systems that were currently used, how did they function? And which of those were essential? So we did some workshops on site with some of the staff, and during one of those, we asked them to just start a pump for us, from scratch, and let us video how that worked. So they took us out to the station. We went through and they started auxiliary systems on some electrical equipment. Then they made sure all the manual valves were aligned for pushing water onto the system. Then they started the motor on the switch gear, which was in a different part of the building, allowed the motor to run up to speed, and then they closed some other valves to bring the pump online, and then finally stop all the auxiliary systems. And that was about a 5-minute process to get everything done. So that was our target for, what we needed to beat for the design. We also did some physical inspections on site. We spent time chasing down big 30 to 50-inch diameter pipes. And one example here is a lower picture. I climbed down into this vault, and I needed to stay on top of the pipes because there's a high water table in New Orleans, and there was water in the bottom of the vault. So this is fairly typical in vaults throughout the country, but in New Orleans it was worse. And then on the right is just another snippet that I think Chris kind of showed a colorized version of this earlier, but just what we had to start with and how much we needed to understand about the complex system of piping at the Carrollton site. Some other inspections we did were, they had existing Venturi meters. They were outside the plant. Venturi meter is a type of mechanical flow meter. These were original to the plant, and they were located in the canal between the east and westbound lanes of Claiborne, and also in the streets to the northeast and south of the plant. They were still installed, and we could have reused them, but we couldn't. We needed to figure out how to put tubing out to the meters, and it was, one per pump station is about how they were laid out. So ultimately, we decided to add magnetic flow meters to the pumps so that we could determine pump efficiency. So some of the design challenges and solutions. From an electrical control standpoint, we spent a lot of time considering system redundancy. We asked questions like, what if there are multiple failures? The system must run under all scenarios, especially hurricanes. This is something that projects rarely consider because double failure scenarios increases the cost exponentially. But this is one where we thought about things like, what if the 25 hertz power failed and we had a 60 hertz VFD out for maintenance? So the left picture here kind of illustrates that. It's a pictorial one line, kind of shows how we designed VFDs that they were custom built that allowed 25 hertz input on one, 60 hertz input on another, but switches on the output so that they could run 2 different motors individually with one VFD. This is one of the double failure scenarios we tackled. One of the challenges we ran into during commissioning was they experienced a low voltage power loss, which turned off the VFD onboard control system and the cooling fans, and eventually shut down all 4 of the VFDs. So after some investigation, we added uninterruptible power supplies, or UPSs, to the VFD control system, and then reprogrammed the drives to leave the VFD running without a cooling fan for 3 minutes. So on a failure like this, an operator would get an alarm, and that gives operations a three-minute time frame to recover from that specific loss of power. So again, redundancy in trying to keep the system online. From the mechanical side, controls mechanical, you've already heard from both of my colleagues about the water hammer issue where we had 30-inch weighted check valves. They'd slam shut on a pump trip, save the pump, but cause the damaging pressure waves into the distribution system. So we switched to a 30-inch actuated ball valve. But one constraint that we had here was this valve had to be able to close at all times, including closing on a complete power loss. So initially, we had planned to use electric actuated valves, but once we calculated the power required for a simultaneous 4-valve shutdown, even staggered, we determined the UPS batteries would have to have been about the size of a semi-trailer at that time. So this was not feasible. It was too expensive and would have required too much to maintain. So as an alternative, we ultimately decided on hydraulically actuated control valves. These run with a very small amount of power, and if all of that power is lost, the hydraulic system closes the valve with the same timing as the control system can do. This is through the use of a hydraulic accumulator on the system. This is just yet another example of adding redundancy into the system and being able to handle any sort of a fault. Finally, for automation, we decided that we couldn't automate the system completely. The pumps are not started automatically. Operations needed to make decisions to decide whether pressure and volume was adequate for the current users, and then bring another pump online if needed. Okay, so we spent years discovering and learning what system they had to work with. So how do we upgrade it in a calculated way, adding for future upgrades? We added a modern control system, and this included a programmable logic controller, what you see here on the screen, some new control panels, a modern network, and another SCADA computer. I've got some pictures of that coming up. So what's a PLC? That's really the brains of the operation. All instruments and devices that are measuring parts of the process are wired into this equipment. And then those signals are cataloged, measured against other signals, and used to make a determination on what to do next. That's the logic part of it. So it's really the brains of the operation. One example here is just the control system commands the new pumps through signals to the VFD to run at a certain speed. And then we measure pressure on the discharge of the system and decide whether to speed up, slow down, or maintain the current speed to maintain a pressure. The system also controlled the discharge valves. So like I said earlier, you could control it on a specific timing curve to mitigate the water hammer effect on the pump and the distribution system. And we also monitored other subsystems like the vacuum priming system that Kate talked about and the seal water system. So once the system was installed and the new system was up and running, we went from a pump starting online in 5 minutes to we could bring a pump online in 45 seconds. So here's the new screens for the operators to use. We placed one of these at each pump so that no matter where in the station the operator currently was, they could quickly come to a pump control panel and check the health of a pump. Here you can see, it's kind of hard to see all the details here, but you can see whether the motor is in and out of service, if it's running, what speed it's running at. You can monitor motor temps and vibration, pump pressures, flow, and the discharge valve position. Here's the SCADA computer that's in the operator control room. SCADA stands for Supervisory Control and Data Acquisition System. So this is a computer that reads what the PLC is telling the system to do and also pulls in other variables. Just a couple of screens here that I had snapshots during commissioning showing the Claiborne pump station. And eventually operations will be able to view all 8 pumps in all 3 stations from this computer. But right now, Claiborne's the only one that's online. On the left, we have a screen showing the clear well level below Claiborne, as well as all 4 pumps, the valves and the flow meters, and what the elevated tower height is for water level. And on the right here, we just have a shot of the electrical layout of the VFDs showing how they're connected to the motors, because remember I said we could switch between 2 motors, and then what the temperatures are in the VFD building, because heat rejection is very important in that building. So instrumentation installation, on the left here, this is another view before the meter vaults were built, showing the magnetic flow meters at the output of each pump in Claiborne Station. There was not nearly enough room in that station to put these are 30-inch flow meters into the station, so we had to put them in a vault outside. That monitors pumps for daily flow, and we can trend them over time to see potential issues or see what the totalized flow is. At the center, we have just a new pressure gauge alongside a new pressure transmitter, so we can see pump discharge pressure. There's one in each of these pumps for operations. And on the right, the vacuum priming system. This is just monitoring the vacuum produced. And then up at the top here, you see some level switches in blue. Those tell us if the pump is full of water to the top. Variable frequency building. So this is the inside of the building. I'm just showing a couple of the VFDs that we have here. There's 4 in this building, 1 for each pump. We had 2 25 hertz input VFDs and 2 60 hertz VFD inputs. So again, redundancy, if 60 hertz power is lost, they can generate 25 hertz power and we can run half of the station. So some of the lessons learned from the controls effort, determine how much to automate. Some of these systems are just simply too complex to automate. And so if they're being designed from scratch, maybe you could automate them, but retrofit designs are usually very complex. And this one was definitely right up there. Flexibility needed during equipment startup. Some of the changes were needed on the fly, and some system operations look really great on paper, but then you need to be willing to refine them and adapt to the given conditions when you're on site. Equipment training, there's never enough training for staff. We had training provided for each of the equipment pieces, and we even had operations shadowing contractors while the system was being built. But there's still questions that pop up from time to time on how did we envision this scenario going? Or maybe what was the system supposed to do? And finally, too much technology, too fast to meet client needs. They were used to running a system without any screens, no control system. So the technology leap forward was huge, and we just had to consider what was needed, versus what technology is out there. So that's what we learned over the course of this. So I'm going to turn it over to Chris to wrap us up.
All right, thank you. And so we're 12 years into this program, and we can see the ending in sight. Middle of next year, we should be complete. And I said earlier, just we've seen the immediate benefits of this. With the water towers by themselves, we've mitigated, I don't know how many boil water advisories, but we know there were certain events where we believe we would have seen them. And then with the improved efficiencies of the Claiborne pumping station, if you recall earlier, our original surge analysis showed we were running 5 pumps and what would happen if we lose 4. But we're now at a stage where we can get by running 3 pumps instead of 5. And a lot of that has to do with the new pumps at Claiborne being that much more efficient with their output. And a huge testament to that was in 2021, we had Hurricane Ida again really devastate this region, although New Orleans itself was spared from much of the damage. The entire metropolitan area was without the local utility power for over 2 weeks. There was not a single light on in the city except for the Carrollton water plant, and we were the only utility in the area to not have to issue a citywide boil water advisory during that event. So it was something we were very proud of as a utility, and I doubt we could have gotten through that way without this program in place. So now that this is starting to show its final form, what can we do in the future? And Scott talked about those limitations on the automation, and we're in the middle of an entire retrofit of our power generation system, a $300 million program that would really try and push us towards getting rid of that 25 hertz power generation system. Now the demand is still 25 hertz with our pump, with our drainage system. So that's a lot of the logistic troubles that we have on that. But once that is done and we have this new system, we could then start talking about automating these pumps. And that is a big reason, is because we rely on our own power so much. These pumps couldn't be automated to start up and shut down, mostly because of the generation side of things. So the future is bright on the pumping side of things, but there's still a lot of work to be done on the treatment side of things, as uh, we as utility know that there are things coming, like the different PFAS regulations and lead and copper rules that we have to work on, and those are huge programs that we have to figure out in the near future. So with that, I'm going to turn it back over to you, Dr. Other.
Thanks, Chris. Thanks, Scott. Thanks, Kate. Fantastic presentation. We learned a huge amount. Maybe what I'll ask is if we perhaps maybe stop the screen share, because then folks will be able to see people's face. And maybe I'll encourage Kate, Scott, to come back on videos that folks can see. So I've been grabbing some questions out of the Q&A panel. I see that you've been answering some of those along the way. Thank you so much. And so I'm going to just lay out what I think would be some nice questions for us to discuss. And then we'll kind of come back and look at these. And so, Chris, early on, some of these will kind of come more to you, and then a little bit more Scott and Kate, and then a little bit more overall. And so, and everybody can feel free to jump in, but I'm just kind of laying out. So first of all, up front, Chris, it's kind of the water supply and treatment, right? So some folks had some questions about, New Orleans having a history of being a pioneer in using advanced instrumentation to look at the quality of raw water, thinking about organics, thinking about activated carbon as treatment systems. So people were curious about that. Then there's this water distribution system and its leakingness. And so, the question is, are there backup generators? Do these pumps have, obviously you got the 25 hertz, the 60 hertz, the steam, but are there backup systems there? What's the composition of that distribution system? And is this cast iron? Is this a mix of everything, including wooden pipes? And when you've got this 60 million gallons of leaking into what is this bowl in these levees, right? Do you have to pump that 60 million out every day as it leaks into the city? How does this distribution system affect water quality at the point of use, right? So distribution system modeling, booster chlorination, and then, kind of Chris, last one in this space that'll be more for you as background. It seemed that FEMA's involvement was great in terms of having some money and all, but it also seemed like it added some policy hurdles, right? Some extra approvals. And so if you can maybe speak to that a little bit, then we'll kind of transition into some of the discussion around actually the builds, right? So, how were the towers sited? How did you tie together all the different utilities that were there? There's power, there's water, there's sewers, there's the transportation, the foundations. How do you keep these things with all this water from continuing to settle? And how was that particularly considered? That's probably more of our civil engineering colleagues, about how do those towers actually not suddenly just sink down into the mud under the city? Scott, you did a great job explaining controls for us. Thank you so much. That can be a weak area for some of us that maybe think more in some of the hydraulics or physical. So fantastic there. But of course, how do we integrate these pieces together with what operators know, and how are operators engaged in, well, what should the controls be? So maybe speaking to that a little bit. And then finally, kind of at the end, maybe if we come back to a couple of broader questions, sustainability. I think many of us in the environmental profession think about municipalities dealing with greenhouse gas equivalents. And we think about, the street lights, and we think about the fleet that the city maintains of vehicles, right? And of course, pumping of water and sewage is a big electric greenhouse. But boy, for New Orleans, it must be a huge part of your footprint to think about all the water you've got to move around. So how does the city think about that in terms of sustainability? And what does that mean as it continues to have subsidence and all, as sea levels rise? How are those things being factored into long-term? And then, of course, the big question, what's the most challenging aspect of the engineering, right? You're taking, 100-year-old plus state of the art then and integrating it with, stuff now. I'm only imagining, Scott, you thinking like you guys are into turning valves by hand, and I'm talking about having it on my smartphone and answering it remotely. How do you bring those things together in an efficient way? So that's kind of the stuff we'll run through. Chris, maybe we'll come to you, and certainly Scott and Kate can hop in, but treatment, raw water supply, that distribution system. Can you speak to some of that? What's currently going on in New Orleans for thinking about the quality of the raw water, thinking about the treatment, dealing with this leaky distribution system? If you can speak to that a little bit.
Sure. Our raw water supply is really fascinating in a a countrywide situation where there's a lot of the country trying to figure out how to get water to them, period. And we are sitting here with enough water to supply the entire country with, just running by our city every day. That is the volume of the Mississippi River that comes by New Orleans. And so we are pretty proud of our treatment facilities. There's really not that much concern of our quality when it comes to the river. As although I know that's kind of a popular thing here, saying we're getting the discharge from every sewage treatment plant along the river upstream, but those regulations are so strict on what you're allowed to discharge into the Mississippi River. So that's not really something that we see on a daily basis. If unless there's some sort of dramatic event that if there is an oil spill or there is a tanker or something that happens on the river, we do have the ability to either pause, stop bringing in water. We have about 12 hours worth of volume that we can sustain, maybe pushing it to 18 depending on the situation. But we're pretty confident that that's not something we're worried about losing, as long as we have the capacity to pull it from the river. And
And
you'd
so
asked a bunch of questions. So
you've got activated carbon in a backup situation if you need.
we have that ability. We do have that ability if needed. It's not something we do on a daily basis.
Perfect. And now the distribution system, when you guys got out there and you were looking at leaks and all, did you get all the way down to old wooden pipes and find those out there? I mean, you were talking about tens of thousands of leaks repaired. I can only imagine the state of that system.
I can't guarantee we're done with the wooden pipes, but I'm pretty sure we recently did a program that pulled up a lot of the French Quarter, and as the French Quarter is one of the oldest parts of the city, and that if there were wooden pipes there and they were replaced, I'd hope that was the last ones. I would say probably most of our system is still cast iron, at least
Perfect.
on the transmission side of things.
Makes sense.
Or you have your
Sense.
transmission and your distribution.
That 60 million kind of gallons per day that then went up by another 30 that was kind of leaking out in the system, right? So now, does that water then have to get pumped back over? Like you bring it
Every
in?
drop of water that makes its way into the bowl has to be pumped out. That's if you notice, I strategically called everything drainage and not stormwater, and because I think to us it is a difference. There is a difference that the drainage system has to drain the city. It is not runoff. Gravity can't bring it anywhere. And frankly, I could do another 2-hour presentation on just the drainage side of things, if you let me.
But it's literally a bowl, and so what you
It
put
is.
in has to come back out, and you've got to lift it back out.
No, none of that water is going to escape the city unless we pump it.
Fantastic. And what does that do in terms of things like thinking about residence time distribution and booster chlorination, right? Because I was kind of surprised to hear, okay, basically we've got these pumps and that pressurizes the whole system all the time without any standpipes throughout or bladders or water towers. Having been in New Orleans before, I don't recall ever seeing water towers, but it's fascinating to realize, oh yes, wait, how does that impact your finished water quality, or how do you guys also address that with chlorination at the tap? I'm assuming you guys are a chlorination all the way to the tap, and so how does that work for you?
So we did notice that in the past few years, that on the far end of our system, we were seeing that rechlorination requirement. And we added a booster system out there just for the treatment side of things, and then we reestablished an abandoned water tower that we had out in that we call it's New Orleans East, is that eastern side of the city. So that was something we had to revisit, and again, it kind of goes back to that whole idea that state regulatory agencies are now starting to really pull into this and keep the utilities in check and making sure that people get clean water.
Right. And this will be kind of our little transition because Kate, you had the picture with President Biden there, touring the facility. Chris, of course, is the involvement of FEMA for a while. So, maybe that'll be our transition question, from Chris over to Kate, where we're talking about the particular design, designs and builds here. Federal involvement, money, but also oversight. So Chris, can you maybe speak to, did that slow some of the process at times or not too
Well,
bad?
if you consider it slow, that's still perfectly fine for us because none of this would have happened without the federal involvement.
Oh, okay.
So they brought that to the table for us. So whatever they needed us to do, we were more than willing to do it. And even if it took some time to get those approvals done, it was well worth it in the end for us, as long
Kind of
as
like
they
it
were
wouldn't have
willing to
been
be
done,
patient with us.
wouldn't have been done without their money. So therefore it was, you jumped through the hoops that were there. So
Absolutely.
And Kate, when Stanley picked up and then started to work with something that had, federal involvement, and now you're talking about President Biden being there and highlighting. So, how was that for Stanley picking up and dealing with and supporting a client that had this kind of, almost maybe two folks looking at the approvals in a sense, right? A federal level and then a local level. How did that work for you guys?
It's fairly typical. I feel like a lot of the utilities that we work for either are getting funding assistance or loan money, either from their state revolving fund or if not FEMA, WIFIA. So it's fairly common to have multiple stakeholders that you need to appease and making sure you're meeting the deadlines and meeting the requirements. So it was something that we were ready for.
Perfect. Fantastic. How about these towers, right? So how is this stuff all sited? How did you guys pull all together these utilities? How do you keep these giant, massive, filled with water, concrete things from just, it's the classic, when they walk around the university, all the students are like, oh, they built that library, but forgot the load of the books, right? So tell us a little bit more detail about the foundations and how these towers were put together.
Sure. Well, our structural engineers can probably talk about that in a little bit more detail, and Chris can help fill in the gaps. But essentially, the biggest part was relocating all of the utilities out of the way. So you had clear space for foundation span, which is obviously much bigger circumference than the cylinder. But it's all a series of piles. Everything's built on piles. So
you build your foundations. Is that true, Chris?
We don't build anything that's not on piles here. That's not a reality. And it's funny that I'm getting the questions here about the settlement, where here I got the questions that, okay, in 156-mile-an-hour winds, is that thing going to blow over? And that is the legitimate question, especially as a couple years ago with Hurricane Ida approaching rapidly. That was the question, as it is within 100 feet of my office right now, is that thing going to topple over? And generally my answer is everything around here is going to be gone and that thing is still going to be standing. The weight of the water in it actually is keeping it upright. Most of the tower failures you see around the country from tornadoes or storms like that are usually when they're empty.
That's what, yeah, I'm guessing you're probably, kind of have an amused smile on your face when they ask you, will the wind blow over our full water tower? So excellent. And so then, so Kate, you were talking about these interacting systems. Scott, you were talking about some of the details in here. I guess one of the questions that was coming online, and this kind of moves us towards the more general question, is how do we put together these legacy systems with the newest modern whiz bang tools, right? In particular, Scott, thinking about, I love that you said we would need like tractor trailers of batteries to be able to actuate this 30-inch ball valve in the case of a power failure. So I can imagine you're just doing those calculations and thinking, oh, wow, that's fascinating. So if you can speak to that a little bit.
Yeah. I mean, there were a lot of things. Actually, I remember the first tour, Chris was there. I was a relatively new engineer back in the day then. And we kind of walked around and said, well, where are the controls? And they're like, that this is all we have right here. So it's very difficult to say, okay, well, where do we start? And then how do we bring them along on this journey, right? And so I spoke about the workshops. We actually did that several times along the way. We would come through a design. We'd say, okay, hey, let's talk to them about this. Here's what we had planned. At one point, we did plan on automating the whole system. And then, like I said, we watched them and videotaped them. And me and another engineer were there. We walked out and we're like, there is no way. That is impossible. We cannot do that. So there was a lot of back and forth on how that worked. And we ultimately decided, okay, well, let's get started with a baseline system that they can run. There's still going to be some interaction here. And then, like Chris said, as they update their electrical system, maybe we can get to a point where it's fully automated, and maybe the operator can just sit in the control room and watch everything. But they're not ready yet at this site, just based on what utilities are there. So
that makes sense. Kate, to you, what was the big, what was the engineering challenge? I mean, there were so many, but if you were going to highlight a few so that folks that are listening in would say, okay, you're right. That's the part that would be the big challenge here. What's your takeaway message for everybody and the big engineering challenge of this project?
I think, as mentioned a few times, it's very easy to design things on paper and it makes sense on paper. It's really when you get into construction, being able to adjust quickly to changes in the field and being able to get all stakeholders, including the contractor and the owner, operators involved to understand important changes that need to happen on the fly and getting consensus on that. So whether that be utility relocation or learning that a control is not going to work exactly according to plan and how can we pivot. It's really staying calm and collected throughout the construction process and being able to work together.
Fantastic. Thanks. Chris, I'm kind of curious. I mean, of course, being there at the interface, having consultant to then having the utility that you're working for and trying to manage that, I'd be kind of curious what your thoughts were the engineering challenges and how those were addressed.
So and this is usually the case for all of the things we do, it's trying to merge that 100-year-old, infrastructure, and I don't mean to say this in a certain way, but the mentality as well, right? There's a bit of inertia when you're talking about what Scott was talking about, this older stuff that just worked. That was the idea. It just worked. We flipped a switch, it turned on, it worked. There's a lot more controls, there's a lot more alarms. It's trying to balance that where I do get calls, I do get texts saying, hey, this tripped, why? And that is the current challenge for us.
They don't want this
I'm
early warning. No, that makes sense. So great. Now it kind of is a little bit tangent, but I'm sure it's very interesting for some of our members to think about. Chris, I had highlighted this idea of the greenhouse gas kind of equivalence, right? So again, when you think about municipalities and you think, street lights and the fleet and the power associated with moving water and all. So if you take a step slightly broader and think sustainability, how is New Orleans fitting this system into their broader goals of sustainability and thinking about how this, how does moving all this water fit into what they're thinking about in terms of climate change and greenhouse gas emission equivalents and the power that's needed to run moving all this water? So
that's a big question, and we do get a lot of questions about it on the sustainability side. We're building a brand new, we're building a power generation facility with combustion turbine generators, and that question comes to us. Well, that's not a sustainable power generation, and to us, reliability and redundancy are primary goals, because if we don't have that redundancy or reliability for power, then the pumps don't work, and well, all the sustainability in the world isn't going to save you when you have a couple feet of water in your city. So we're trying to balance that. That is the hard part for us. We're trying to balance green infrastructure to try and hold the water in places that we can, so we don't have to pump it out. It's been well documented that us basically drying out the city for decades caused some of that subsidence. And so how do we balance that? And it is challenging because we do have our canals throughout our city. We try and keep them low because our storms in this city aren't really that predictable. As you know, the other day on a just sunny Saturday, in comes a storm from the lake, and it dropped 2.5 inches of rain on us in about 45 minutes.
Wow.
On a certain neighborhood. So if you're not prepared for that, you're not going to survive it. So it is a big question, and we have an urban water plan. We have working with all of our local stakeholders on these things. So it's a challenge for us, to say the
Thank
least.
you. Well, Scott and Kate and Chris, thanks for joining us today for this webinar. Thanks to our patrons for financial support. And of course, thanks to Stanley for financially supporting this webinar for the Academy. We'll turn it over to Marissa to close us out.
Thank you so much, everyone, for your questions. And thank you to our 3 speakers for sharing your knowledge with us today. If you have additional questions on this topic, please reach out to me and I'd be happy to put you in touch. We do have several webinars planned in the near future, so you can go to aaees.org/events. You can check them out there and register. And if you're interested in sponsoring an upcoming webinar, please reach out to me directly. My email address is mwaterman@aaees.org. Just a reminder, if you're not yet an AAES member and you're considering joining the Academy, please email me and we can discuss our membership options. And last but not least, the PDH certificates for this event will be sent out shortly. That's all for now. We enjoyed being with you all today. Thank you so much and have a great day.